Hey everybody, so before we actually get into the halogenation of aldehydes, ketones, and carboxylic acids, I first want to review what the general mechanism is for the alpha carbon substitution. So a lot of times in our class, we go through the general mechanism, so then it helps you apply that to a bunch of different scenarios that we have. And so the general mechanism is that if we have an acid or base catalyst, we'll assume an acid catalyst. We start with some arbitrary carbonyl compound, either ketone, aldehyde, potentially a carboxylic acid as well. And when we add the acid catalyst, last lecture, we talked about how this will then generate the formation of the enolate, or not enolate ion, but the enol tautomer of our ketone or aldehyde or carboxylic acid or carbonyl compound, right? And this compound right here has this electron-rich pi system between the two carbons here. I'm going to erase this carbon here just to keep everything in the carbon skeleton that I used in the first part. So we have this electron-rich alkene region, which is very reactive. And if we have an electrophile in solution, we will get an attack of this electrophile by the alkene or the double bond, right? And so when we get this attack, what's going to happen is we're going to generate a double bond between the oxygen and the carbonyl carbon, so that we don't generate an intermediate carbocation in this reaction here. And so once we have that, this will then we have a protonated carbonyl oxygen, which isn't very stable, which is probably going to be our intermediate step. Our alpha carbon, I'm going to draw explicitly here, is going to be then bonded to the hydrogen, our R prime group, and then now also this electrophile. And then if we have conjugate base from an adds to the catalyst in reaction, or potentially base in the reaction itself, it can then come and abstract. So I'm just going to use A minus as whatever our base is here. It can come and abstract this hydrogen to then finish the substitution of this reaction here. And so when the base abstracts the hydrogen, the protons are going to move back onto this is going to be R here. Protons are going to move, not the protons, the electrons are going to move back onto the oxygen, and then we have our now substituted, alpha carbon substituted compound. Right, so the first step is in this step right here, we generate the enol tautomer. Then once we have the enol tautomer, that can go through a nucleophilic attack of the electrophile. We then add the electrophile, right, because this is and eliminate the double bond, but originally we started with something that doesn't have the double bond, which is why it isn't an elimination or addition reaction. It's a substitution because we're just substituting for one of the spots on the carbonyl, or sorry, on the alpha carbon there. Originally, we started with 2 hydrogens. Let me see if we can get a laser pointer. We started with 2 hydrogens here. And then at the end, we only ended with 1 hydrogen there, right? So in the generation of the enol tautomer, we lost one of the hydrogens to create this double bond. So that's where we got rid of a hydrogen. And then through the mechanism of then reforming the keto tautomer with the addition of base to then generate again our ketone or carbonyl compound. Right, so that's why this is a substitution reaction, because we're substituting one of the hydrogen positions here. And so this is the general mechanism for the alpha carbon substitution reaction.